Welcome to this class. There are several applications of operational amplifier that we have seen until now, and there are a lot of applications which we can still use op amp for. We will see in today's module a very important application of an operational amplifier, and that is voltage control current source. Voltage control current source. So, what exactly voltage control current source means? That if you by changing the voltage you can change the current. By changing the voltage you can have the you can design a current source, and you will see the current source voltage control current source not only on the breadboard, but also using multisim. Both the ways we will see, and we will see the low current application, high current application. So, on the breadboard probably we will see high current application, and on the multisim we will see a circuit which can be used for low current application. Now, when you talk about current source or voltage control current source, what is the application of voltage control current source, right? Is there any other thing like constant current source, constant voltage source? If yes, where are they used? If it is voltage control current source, what is the application? If it is a constant current source, what is the application? Constant voltage source, what is the application? So, try to understand as much as you can, try to find it as much as you can. Alright. So, for this particular module, let us see what exactly voltage control current source is. Alright. So, if you come on the screen, you see that for many applications one may have to convert a voltage signal to a proportional output current, right. Is nothing but V2I, voltage to current converter, right. So, hence a bipolar current generators may be required. We need to require current. So, current generators are required. These are called current sources. These are called nothing but current source. Alright. A unipolar current generator or source is either a current source or a current sink. It can either source the current or it can sink the current, right. So, if it current source, then it generates the outflowing current. If it sinks the current, then it generates the inflowing current, right. Here unipolar means that it can produce currents flowing in one direction only, usually towards the ground. That means, if you look at this particular circuit, you know that the voltage, there will be some voltage over here which can be generated using a potentiometer, Now, you know a concept of virtual ground. We have already seen what is virtual ground. With the concept of virtual ground, whatever voltage is here, same voltage will try to appear over here, right. Same voltage try to appear over here. Now, what is this? The circuit is nothing but a voltage follower, So, when this happens, that means that this transistor conducts, and the resistor, the current across this resistor, right, it depends on the voltage that is we have applied over here, because it is trying to follow the same voltage. Depending on that, if you have your emitter current here, then the same current will be there in the collector, same current we will have in the collector. So, if I change this, keep on changing this voltage, I will constantly be able to see the change in the voltage across this resistor, and this change in resistor will keep my current constant, will generate my current, will keep my current across the load resistor flowing, because this transistor is in conducting state, transistor will be in conducting state. One thing you have to remember is, in the high power application, this particular resistor should be 10 watt 1 ohm. But we will see two different application of this voltage control current source. One is in high power and second is in low current applications, alright. So, we will see two different circuits as well. First thing is, now you understood how the circuit operates. Then unipolar, as we have discussed, it is only that it will follow in from the source to the ground, it has to go to ground. A voltage control current source or sink may be designed using operational amplifier. This is nothing but your operational amplifier, right. In such a circuit, a precision and a stable resistor R1 defines the output current I out, right. Stable resistor R1, right, this one defines the output current I out. Okay. The circuit contains a feedback loop through the op amp that keeps the voltage across R1 constant. Now, you can see that there is a feedback across the operation amplifier, because of which the voltage across this R1 is constant, right. Now, to deliver a higher current at maximum voltage compliance, voltage drop as small as possible should be developed across sensing resistor. Voltage drop as small as possible, how we can develop this kind of voltage drop, because we know that the value of current here, or V equals to IR, then I equals nothing but I equals to V by R, right. That means, if I want to have a higher current, then my resistance value should be extremely small, resistance value should be extremely small, and that is why what we have earlier shown is that the current here, the resistor here is high watt resistor, power resistor with a resistance value of 1 ohm, resistance value of 1 ohm. So, in effect the current is equal to V by R, current is equal to V by R, right. So, for better performance, the current through the base of the output transistor should be minimized, hence a field effect transistor rather than BJT is often used, right. The current through the base should be optimized, or it should be minimized rather, right, and that is why instead of the BJTs, if we use FETs, it is better. So, if I want to design this voltage control current source, right, then how can I design? One way is of course this one, which is right in front of you, right. In high current application we can use this particular circuit, but what if I want to use a circuit for low current applications? For low current applications, I can use this particular circuit, which you can see here, and it is nothing but voltage to current converter, right. And if I want to use the op amp as a so this is all are grounded load, you see the loads are grounded, right. Load is grounded here, load was grounded earlier, right, but here what I have to use here, if I see this particular circuit, which I call as B, this is I am calling as A, and this is I am calling as C, alright. So, if I use this particular circuit, which is my B and C, I see there is a floating load, you see the load is floating, here also you can see the load is floating, right, it is not grounded. In this situation, whether I am using inverting or non-inverting amplifier, that is another case. So, this B is showing a non-inverting amplifier, the voltage that is given is across the non-inverting terminal. In case of the C, the voltage is generated at the inverting terminal, right. So, now I have 3 different circuits, one is the voltage to current converter with grounded load, one with floating load, and with inverting configuration, non-inverting configuration and inverting configuration, right. So, what we will do today is we will see how we can design this particular circuit, this one with multi sim, and the previous circuit, that is this one, on our breadboard, right. So, 2 things we have to do in this particular experiment to understand the voltage controlled current source is, one, we will design the circuit using breadboard, and second we will also see using the simulation, So, if I want to perform the experiment, the aim would be to study the working of op amp, based on voltage to current converter, alright, voltage to current converter. So, if you see, this circuit is similar to what I have told earlier, where you have to use this resistor, which is a power resistor, and that is why the value is about 10 watt 1 ohm, 10 watt 1 ohm. The connect the circuit as shown in figure, okay, we will connect it. Here R1 is 1 ohm, which is here, this one, and 10 watts. So, maximum allowed current, right, is 3.2 ampere. Maximum allowed current would be 3.2 ampere because I square R equals to P. So, I equals to under root of P by I and that is why 10 watts by I, which is your, so 10 watts by 1 sorry, because 1 is your resistor, right. See, I square R equals to P. So, we can write I equals to under root of P by R, right. So, I equals to what is power? Power is given, power is 10 watt, resistance is 1 ohm. So, 10 by 1 ohm. If you do this mathematics, simple mathematics, you will understand I would be 3.2 ampere, which is the current, alright. So, this we know, alright. Now, next what? Apply a DC voltage, input voltage, DC input voltage from where? From here, alright, of 0.5 volt and slowly increase the voltage a step size of 0.5 volts. We will apply 0.5 volts and we increase with a step size of 0.5 volts. Observe the output at the current I out, observe the output here, alright, and calculate the relation between output current and input voltage. We have to understand what is the relation between input voltage and output current. So, we will have 1, we will have 2, we will have 3. Let us see input voltage what we apply, right. DC input voltage starting at 0.5 volts, we will start at 0.5 volts, then we go on increasing it and we look at the current at the output, right. So, to perform this particular operation we will design or implement the circuit shown in figure 9, which is right over here in your on your screen, and we will implement this circuit using the breadboard, So, when we want to implement circuit within breadboard, let us see how it will look like, and we will ask Sitaram to join us to show us how the circuits, how this circuit can be implemented using the breadboard, how the circuit can be implemented using the breadboard. So, now you can see, if you see the circuit, right, the green big boy is your resistor, is a power resistor. You can see it is 10 watt, right, tolerance is plus minus 5% and the value is 1 ohm, right, value is 1 ohm. And then you can also see transistor, right, is a power transistor, and you have the heat sink. Why there is a heat sink? Because a huge current is going to get generated, and if it flows through the transistor, right, the transistor will get heated up, and to dissipate this heat we require the heat sink. Now, what we have to use? We have to use a operation amplifier. So, we have to apply plus minus 15 volts across the breadboard or across the op amp. That is your bias voltage, So, we will use the multimeter, to measure the current, because we already know how much voltage we are applying, because we will apply through the DC power supply, which is 0.5 volts, right. So, and then we will keep on increasing and we will see the change in the current. Okay. So, we have to measure the current at across the load resistor, and we can see the current on the multimeter. We will be able to see the change in the current on the multimeter as well. So, now we are connecting the voltage, we have connected the voltage. So, we are connecting the voltage, DC voltage at the input of the voltage, to current converter, Okay. Now we have to start our power supply, right, DC power supply, DC power supply. So, we will start the DC power supply, right, and we will increase in step of 0.5 volts. So, first we will apply, we are applying right now plus VCC to the transistor, applying plus VCC to the transistor, and you can see plus 15 volts, okay, and we are applying the same way. You can see when we are changing the voltage, the current increases, the current increases. So, let us not go with very high current, yeah, okay. For 0.25 volts you can see there is a current of 0.20 or 0.19 ampere. You can see in the DC power supply also, you can see in the multimeter also, right. You can see in the multimeter right now it is in amperes. So, it is 0.20 amperes, 0.20 amperes, right. If I reduce the voltage, if I reduce the voltage, yeah, it is 0 directly, but can you increase it slowly? Oh, okay, 0.7, you can see the change in the current, alright guys. So, this voltage to current, you see voltage to current, it is converting your voltage to the current, it is converting your voltage to the current. There is some loss, there is some loss, and that is obvious, that is obvious because of the circuit. There are components, we will have a lot of voltage drop across the components, and you can see basically the loss is due to the transistor that is connected in the circuit. But anyway, the point is that now we have designed a voltage to current converter with a simple circuit that you are looking at here. The main point that you have to find it is that you have to use a power resistor, you have to use a power resistor, you have to use a power transistor with a sink, right, with a sink. You can see at 0.5 volts we have 0.39 volts, 0.39 amperes, right, 0.39 amperes. Thus, this is the way that you can design the voltage to current converters, alright. So, we can, I am not writing down on the screen, but I am showing it to you here how we can implement actually voltage to current converter, and how we can see this voltage to current converter working, alright. Now, if I want to do the similar study, if I want to do the similar study with multisim, but in multisim let us see the circuit which is for the lower current, which does not require high current, alright. So, for that one, what was the circuit? The circuit was this one, which you can see here, which is multisim, MULTI, multisim, alright. So, we will implement this particular circuit, and we will see that what happens when we change the voltage, and we will see the change in the output current, we will see the change in the current at the output, okay. So, for performing this experiment, we will open the multisim, and of course, Sitaram will continue, he is here. So, we will again open the multisim software, we have opened a new file, and we have to design the circuit which is V to I converter, right. So, now you all are expert in using multisim. So, you know what we are doing here, we are dragging the resistors from the library, we have already dragged the op amp, right, and we have to just use different resistors here. Now, this is a low current application, that is why we are not using a power resistor in this multisim, okay, we are not using power resistor. So, we are adjusting or we are writing down the values of the resistor that we want to use, right, 10 kilo ohms. We have our op amp ready. Our load resistor is 1 kilo ohm, and now as you see what will happen, as we change the input voltage, you see input voltage, the output voltage follows the input voltage, output voltage or we can the output current, here we are measuring the current, right, voltage to current converter. You can see the output current, right, it is depending on how much voltage we are applying at the input. This voltage is converted into current, and you can see that the voltage what we are applying is getting converted into current, and is a low current application. That is why you cannot see current which were like 0.3 ampere or 0.4 amperes, right. Here you are looking at microamperes to milliamperes. Again, if you drag it slowly back, then you will see that as you change the input voltage, your current output at the current at the output also changes, and in short the circuit is nothing but your voltage to current converter, voltage to current converter. So, if I change the value, if I change the value of the load, right, in that case what happens, in that case what happens, I can still follow the voltage. You can see the voltage we are applying at the input and the output is the current. So, we can see that the output current is getting generated by the input voltage applied at the non inverting terminal, right. So, this is how you can design, this is how you can design a voltage to current converter, in multisim, right. So, so if you have seen what we have seen here is nothing but the voltage control current source or voltage to current converter, right guys. So, this is the application, of the operational amplifier, this is the application of the operational amplifier which is the voltage to current converter, right. And we have seen two things here in this particular module. One is the voltage to current converter using the breadboard, and second was voltage to current converter using multisim, right. So, I hope you understood what we have discussed in this particular module, right. I hope you have understood in this particular module, and you have to understand this particular video, understand how voltage to current converter works and see the application of voltage to current converter. And what I feel is that once you understand how the voltage to current converter works and see the application, try to see the same application for all the other modules that we have previously discussed, alright. So, if you really understand all the topics that we have discussed till now, you will find that we have discussed huge amount of applications, right, or large amount of applications, starting with the basic thing to coming to this kind of circuits where it can convert your voltage to current. So, now understand what is the application of solar cell. If I have a solar cell, what is the output? And if I have a photodiode, what is the output? Can I convert my voltage to current? Voltage that is generated, can I convert to current? So, I have given you some hint, but you have to find out the real applications of the circuits that we have discussed during entire series of the modules, particularly the experimental part of this particular lecture. Alright. So, I will see you in the next class, and that class will be the final class for the experiment portion and final class for this particular course as well. So, read it, right, understand it, look at the video, right, try to figure it out, try it using multisim at least, right. If you do not have the equipment, forget about it, at least use multisim. If you have multisim equipment, please use both. The recommendation from my side would be theory, simulation, experimentation, right. But if you have no experiment, if you do not have the equipment, do not worry, at least perform simulation, alright. So, with that I will see you in the next class. Till then, you take care.